So let's continue our discussion about fluids and fluid dynamics. We're going to start off by talking about Archimedes' principle. Now, this was the principle supposedly discovered by the Greek scientist Archimedes, who apparently jumped in the bath and upon realizing that the bath then overflowed, came to the conclusion that solids displace fluids. In all likelihood, this story is apocryphal and was probably invented so that he could explain the principle of displacement to people who had little scientific knowledge. But anyway, this still works. Fill a bath almost to the brim and then climb inside. You have mass, therefore you have weight. Your weight will displace a volume of fluid, which will then overflow the bath and make a mess on the floor. Make sure you're not upstairs. So Archimedes' principle that he apparently came up with through this method states that any object completely or partially submerged in a fluid is buoyed upward by a force whose magnitude is equal to the weight of the fluid displaced by the object. So what does that really mean? So let's just take a look at a generic cylinder here placed into the bath. So we have a container. Here's our container, and here's our cylinder placed into the fluid. I'm going to refer to it as water here, so I don't keep saying the fluid. So our object is placed into a container of water. Our object has some area A, and will experience a force of gravity here due to its weight. So weight will be equal to mg. This object, when placed in the fluid, will feel a buoyant force, Fb, upwards. So our basic equation becomes delta P, a change in pressure from the top of this fluid to the bottom of where the object sits, times the area of the object is equal to weight, W, which is mg. Delta P will be P bottom minus P top times A. This will equal W, and that is the condition for an object to float. If delta P times A is equal to W, the object will float. So Archimedes' principle really states that the buoyant force here, Fb is equal to delta P times A, being equal to the weight of the displaced water, is exerted on the submerged object. So our buoyant force is equal to the weight of water displaced. So the more buoyant force, the more water will be displaced, and the higher the water level will become. When you place an object into a fluid, quite often it won't either sink or just sit right perfectly on the surface. The object will usually sink slightly to some level and then stabilize with the water either halfway or some fraction up the object. So an object will sink to a level where the buoyant force always equals its weight. So Fb will equal mg. If Fb is less than weight, if Fb is less than the weight, then the buoyant force is insufficient to hold up the object, and it will sink to the floor of the container, or the seabed, or whatever body of water it happens to be in. Just as an aside, water exerts about 10 newtons of force per litre. So for every litre of water you have, you're getting an extra 10 newtons of force. So that means 1 litre of water displaced in this case will give a buoyant force of about 10 newtons. So our buoyant force, of course, as we just stated, was delta P times A, and that will be equal to the weight of water displaced by our submerged object. That means delta P times A, as I stated in the previous slide in words, is equal to mg, or P bottom minus P top is equal to mg, and that's the condition for our object to float. So our object will always sink to the level where Fb equals W. So this is essentially the same thing, just in words. So if our buoyant force is large enough, it'll support the object's weight, and the object will displace just enough water, so FB is equal to W. If the object displaces as much water as possible and does not equal its weight, the object will sink. It's the condition we said before. Now, what this means for us is objects with less density will float in water. So objects with a reduced density tend to be the ones that float. That means in the days when people were launching the first iron ships, everybody said it was fairly obvious that an iron ship is just going to sink. We know this isn't true, as steel and iron ships often float around the oceans today. The reason behind this is people didn't understand the concept of density. If we take 200 tons of iron and throw it into the ocean, it will of course sink. If we take 200 tons of iron fashioned into a ship's hull in thin sheets and with the mass spread out over a volume, then the density is reduced and the ship will float. Another effect is that when an object is fully submerged, buoyant objects will weigh a little less in water than they will when they're on the dry land. So you can kind of see this effect if you put a very heavy object underwater, even such as a person, and then you can lift them much more easily underwater due to their buoyant force. Get them to the surface of the water, they become much heavier. So let's take a look at an example. Here we have a 140 kilogram piece of equipment with a volume of 0.09 cubic meters lying on the seabed. What is the minimum force required to lift this object? And we're going to assume the density of seawater is 1.025 times 10 to the 3 kilograms per cubic meter. So this object will of course have a weight, that's a force due to gravity acting down on it. It will also have a buoyant force acting upwards on it. So we need to calculate how much force we need to get this object to lift. So here's our piece of equipment, and the force is in the y direction will look like this. We'll have mg downwards, this is our weight, negative mg, and a positive FB, a buoyant force that's going to reduce the force needed to lift this object. So the buoyant force on the equipment is equal to the water displaced, or the force of the water displaced. We know this much from Archimedes' principle that we've already discussed. Other things we know the volume, we know the mass, we have a density, we want to find F. Now with any force problem, your first place to call should always be F equals ma, Newton's second law. So applying F equals ma, we can say that all the forces in the y direction we're going to set to 0. Now what we want is the minimum force required to lift the object. So we're going to find the force just before the object starts to lift. So by setting everything to 0, this will be the point at which FB equals mg, and that will be the force we need to beat to lift this object. So if we actually write out all our forces, we're going to have F plus FB minus mg will be equal to 0, or the force we require is going to be mg minus FB. Always draw the diagram. This expression here comes from these vectors. So what's FB? Well, it's ma, which is m times g. The mass of water that we have here is 140 kilograms. Well, sorry, the mass of the object, the equipment, is 140 kilograms. G is 9.8 here. We also have the situation where we don't outright have the mass. Well, we have the mass, but we don't have everything in the terms that we want. We can say that the mass of H2O that is displaced is going to be equal to rho Vg. So we can substitute in here for m. So Fb becomes mH2O, how much mass of water is displaced, times g, which is rho Vg. Substitute in rho, which is our density of seawater. Here's our volume. Here's gravity. Will give us an answer of 904.05 newtons to lift this object. Now, the force, if we go back here for a second, this is FB. This is the buoyant force acting upwards. The force on the mass due to gravity is 140 times 9.8, which will give us 1,372 newtons. So now we have a buoyant force and we have the weight. So, incorrectly stated in the previous slide, the force required to actually lift the mass is the difference between mg and the buoyant force. 1372 minus the 904 in the previous slide will give us a 467.95 newtons that we need to inflict to lift the object. This being about, if we look at the ratio, 2.93. So this thing weighs about 3 times less here underwater than it will once we get it above the surface. Now, here's a question I wouldn't normally ask, but this is the kind of thing that pops up on a lot of exams like MCATs and other placement exams. So, if we look at this problem, we're saying what is an object with a volume of 6 litres and weight of 30 newtons if it's placed in a tank of water? Will the object sink or float? Furthermore, what fraction of its volume will be submerged if it floats? So same situation as before. Here's weight acting downwards. Here's buoyant force acting upwards. Okay, so first of all, if the object is completely submerged, the buoyant force will be, and we already know how many newtons of force we get per litre of water, and we know we have 6 litres. So the buoyant force is 10 newtons per litre times 6, which is going to give us 60 newtons. The object will float, therefore, with about 50% of its volume submerged. How do we know this? Because FB equals mg equals 30 newtons. So we have a weight of 30 newtons, a buoyant force of 60. This is roughly half, or not roughly, it is half of this. That means this will float at about 50%. And this is generally true of the calculation you can conduct with any particular solid. The only thing that is a bit strange is water itself is weird, which is annoying since it's the most ubiquitous material almost on the planet. Water is dipolar, and we're going to discuss this in a bit more detail later, and it expands as it freezes. That has the odd effect, meaning that the density of water ice is 917 kilograms per cubic meter, whereas the density of liquid water is 1000 kilograms per cubic meter, meaning that water ice is slightly less dense than it is in its liquid phase. That has the odd effect of making the solid phase, making the solid float on the surface of the liquid. Now, if anyone wants to see this done wrong, go and watch the very first G.I. Joe movie. Hilariously funny for all of the wrong reasons, as a secret Cobra base underneath the ice ends up being bombarded by ice falling down onto it when the good guys blow up the ice and make it fall onto the base. This would obviously not work, so very funny for having a look at the bad physics. And I will often be pointing out bad physics in movies as we go. So if we take something like an iceberg anyway, taking this principle into account, less than 10% of an iceberg's total volume actually floats above the surface of the water. And this is part of the worry with such things as global warming, in that if the ice does completely melt, that's a lot of fluid that's going to be contributed to the overall sea level of the world. So let's take a look at an example here. Here we have an ice cube in water. Now bear in mind that this is just a small cube rather than an enormous iceberg. So what I'm about to say is a little different. So as the ice cube melts, will it A, water spill out, B, water level remain the same, or C, will the water level reduce? In this case, the level will remain about the same. Remember, ice is less dense than water, so the volume occupied by ice is sufficient to hold the volume of melted water in this case, and so the volume will not increase appreciably and overflow. So that's Archimedes' principle. That's buoyant forces and displacement. When we are dealing with fluids, here we can look at fluid flow, and this is moving into our next section. How do fluids move and fluid dynamics? So if we take this situation, here we have a tap and some container with 3 holes through it. Now, as we fill this container, water will build up in the container and then, of course, pour out of the holes. If we're to look at this situation, what will happen is the water here will come out at higher pressure than the water here, and this will be at higher pressure than here. We really want to quantify this effect, but why is this happening? Well, pressure will increase with depth. So the speed of the water leaking from the holes is larger for the lower ones than it is for the higher ones. So the pressure here is greater. That means that the water will be ejected with more force at the bottom than it is at the top. So we're really looking at how fluids flow. And if we're talking about quantifying fluid flow, then we really have to look at this in terms of volume per unit time. Quite often, if you look at a water metering system, these tend to be expressed in gallons per minute, GPM. Generally, if we're doing SI calculations, we'll try and put ourselves in the realm of liters per second, or usually cubic meters per second, liters to cubic meters being a nice conversion factor. Gallons per minute is quite a common civilian measure. So this is referred to as a volume flow rate. So when we talk about a volume flow rate, we could have a tube, be a pipe, hose, something like that, of some cross-sectional area that's referred to as A. And we'll have a flow speed which tends to be given as V or U. It's interchangeable. So the volume flow rate will be some velocity times the area. V sometimes, as I said, can be expressed as U because sometimes V gets confused with volume. So be careful with your V's. If we're looking at a volume flow rate, this would be in terms of meter squared, well, meter cubed per second, because this is meter squared times meters per second. Now, if we want to measure the velocity, we need to find the time that's needed to fill a vessel of some known volume from a pipe also with a known diameter. So in terms of mass flow rate, you can express things instead of in terms of volume flow rate, in terms of mass. So you could, if you knew the density of water, convert your previous expression here in terms of volume into a mass and have a mass per unit time flow rate. That tends to be more regular in terms of physics. So the mass flow rate would end up being rho, the density of your material, times the volume, times the velocity, times the area. So when we're dealing with the flow of water, we've already looked at a case like this in terms of a water tower next to our house and looking at the pressure of the water ejected. So water will flow under gravity. If you place your water at high elevation, the pressure at the foot of a tower will be sufficient to circulate water to a whole town. The mass flow per second, the amount of mass per unit time, will be sufficient to circulate around an entire community. But in order for water to flow, you do need a pressure differential. And this can be looked on very much as a potential, such as when we were looking at potentials, say, in an electrical case. What you really need is a pressure at one end of a pipe that's different to the other. In this case, we'd have a higher pressure system at P2 and a lower at P1, causing fluids to flow from P2 to P1. So if we want our fluid to flow this way, P2 must exceed P1. If we do it the other way round and P1 exceeds P2, then our fluid would flow from right to left instead of left to right. So a differential can be set up by a water pump. You could say pump water up into a tower, creating a pressure differential, pressurize the vessel itself by pumping in more and more fluid. However you want to do it, you have a pressure differential that causes your fluid to flow from one place to another. Now, what we're moving towards here is discussing something called continuity of flow. Every pipe we're going to discuss here and every waterway is not going to have any leaks. We're going to assume, probably incorrectly for most cases, that there's no holes with water pouring out of them. So what goes in one end comes out of the other. This is referred to as continuity of the fluid or continuity of flow. So fluid entering one end of a pipe must also exit. Here we have some volume entering this pipe with some area A1. You can see this is a larger area, and then it will constrict down to area A2 with a new velocity as it moves through this part of the pipe. So as all fluid entering our system, one end has to also exit. That means A1 times V1 is equal to A2 times V2, where V is the flow velocity, remember, and A is the area. What does this mean? Well, if A is reduced, in order for A1 V1 to equal A2 V2, if we reduce A2, that means we have to increase V2. So fluid in a narrow part of a tube must flow faster than the fluid that's in the wider part of the tube. This is the kind of method that cardiologists use to determine if you might have some kind of clogged artery by looking at the flow through the blood vessels. So this is essentially a repeat of what we just said, but this relation can be written in terms of volume and time. So here we have delta V, capital V. This is a change in volume. A is once again area, and I've made this little v velocity, flow velocity. So make sure you don't mix up the V's here. So delta V, the volume change here that's going to come about in this system is going to be A1 V1 times T, which is A2 V2 times T. And this is the volume that would essentially flow through your system. This equation, A1 V1 is equal to A2 V2, is referred to explicitly as our equation of continuity. So if we talk about the equation of continuity again, this is what we're talking about. So here's the typical situation in terms of using the equation of continuity. Here we have an area A1 and a velocity V1 and an area A2 with velocity V2. This whole thing can be expressed in terms of mass and density. So we're rewriting the previous case that was in terms of volume in terms of mass, because usually what we care about is how much fluid we're shoving through our system. So delta M is the amount of mass that passes a point in the pipe during some time t. Rho is our density of the fluid. We have A, we have our distance, how much of a distance we want to look at along our pipe, so delta X, what's the distance of interest, and this will equal rho A Vt. So the equation of continuity in density, if we take this and derive through, will be ρ1 a1 v1, where this is a velocity, is equal to ρ2 a2 v2, so second velocity. So let's take a look at using the equation of continuity. Let's use it in a practical fashion. So here we have a situation where water is circulating through a house in a hot water heating system. Water is pumped through at a velocity of 0.5 meters per second through a 4 centimeter diameter pipe in the basement under a pressure of 3 atmospheres. The question here is, what is the flow speed and pressure in a 2.6 centimeter pipe on the second floor 5 meters above? And here's a little schematic of a heating system, a general schematic rather than one to scale with this problem, just to show you how this system would work. So first of all, let's list what we've got. We've got velocity of 0.5. We've got a radius, which I've already converted to 4 times 10 to the minus 2 meters. We have a 3 atmosphere pressure. Good to convert this immediately, which is 3 times 10 to the 5 newtons per square meter, or 3 times 10 to the 5 pascals. The rho of water is going to be 1 times 10 to the 3 kilograms per cubic meter. And the question is, what is the flow speed and pressure in a 2.6 centimeter diameter pipe on the second floor? So the first place to go with any problem like this is to employ the equation of continuity. This will give us the flow speed on the second floor. So remember, we were dealing with A1 over V1 is equal to A2 over V2. That means if we want to look for V2 here, V2 will be V1 A1 over A2. We do have to deal with these areas, however. A1 will be pi R1 squared, and A2 will be pi R2 squared, where R1 is the 4 centimeters and 2 is the 2.6 centimeters. Substituting in here and then calculating through, of course these are r squared times pi, will give us about 1.2 meters per second. Here's our velocity, here's our pi r squared for R1, pi r squared for R2. Now, we're armed now with the velocities. So now we have V1, V2, R1, and we have our pressures, we have our densities, and we have gravity. The question is here, what's the flow speed and pressure in the pipe 5 meters above? We just used the equation of continuity. Now we have to use what's referred to as Bernoulli's equation. And this is P2 is equal to P1 plus rho g times h plus 1/2 rho V1 squared minus V2 squared. If we substitute into this equation, we'll then find an answer of about 2.5 atmospheres. Now, this equation, unfairly introduced before we actually talked about it, is Bernoulli's equation. So here's Daniel Bernoulli, lived from 1700 to 1782, so he lasted quite a while through periods of the Black Death and various other things. And Daniel Bernoulli here actually came up with this idea of looking at the continuity flow between 2 points in a pipe, and went through the derivation of his equation by looking at the conversion of potential energy to kinetic energy, looking at the velocity that a fluid would gain if it was actually moving down a gradient or going up a gradient. Here is the derivation that I won't go through in great detail, but any intermediate part of this that we've already seen can be employed. I do realise that the previous example used Bernoulli's equation before we'd introduced it. I would say that after getting over the initial shock of never seeing this equation before, go back in the slides and specifically in the PDF of these slides and take a look at how this equation is employed. But this is Bernoulli's equation and is often used in conjunction with the equation of continuity that we just saw, which is going to be now, for Bernoulli's equation, P1 plus rho GH plus 1/2 rho V1 squared is equal to P2 plus rho GH plus 1/2 PV squared. It doesn't exactly roll off the tongue and not very memorable, but in an exam situation, I would give you this exact equation. It is your job to know where to use it and how to use it. So the summarized version of Bernoulli's equation is basically P, a pressure, plus 1/2 the density times V squared, plus rho gy, density times gravity times the height, is equal to a constant. So this is very similar to results that we've seen before, but just put into a nice, easy to use, or relatively easy to use equation. If we apply our continuity equation to this, then we can put it in terms of Bernoulli's equation and say that P1 plus rho GH plus 1/2 rho V squared is equal to P2 plus rho GH2 plus 1/2 PV2 squared. So let's explicitly employ Bernoulli's equation. So if water is moving through a pipe with a speed of 5 meters per second and this pipe has a cross-sectional area of 4 square centimeters, it will gradually descend 10 meters as the pipe cross-sectional area increases to 8 square centimeters. There's a lot of information in there, and I would literally write these things out. V1 is equal to 5 through a pipe of area A1 is equal to 4, gradually descends 10 meters, which is height, to a pipe of cross-sectional area that is going to be A2, which is 8 square centimeters. What's the speed at the lower level? Well, this is going to be an application of Bernoulli's equation, and there it is stated again. Part B is then going to ask us what the pressure is at the lower level if it gives us the pressure at the upper level. So let's not worry about B just now. Let's take a look at A. So, first part, we want to find the flow rate. So let's employ our equation of continuity. V2 is equal to A1 over A2 times V1. A1 here is the area of the pipe at the top of our system, and V1 is the speed of the water there. A2 is the area of the pipe at the bottom, and V2 is the speed at the bottom. So this is going to be 4 square centimeters over 8 square centimeters times 5 meters per second. Convert the centimeters through, you'll end up with an answer of about 2.5 meters per second. Part B, if the pressure at the upper level now is 1.5 times 10 to the 5 pascals, what's the pressure at the lower level? Now you do have to engage with the full-blown Bernoulli's equation. We are armed now with our velocity, of course, that we just calculated from part A. So if we take a look at this, we can say that P2 here is going to be P1 plus 1/2 rho, the difference in the velocities, delta V, plus rho G delta H. And this is usually the form that you will use to describe a situation and use Bernoulli's equation. So look at this problem in more detail. Look at as many examples as you can about the use of Bernoulli's equation, because this usually reduces down to this delta of P1 plus 1/2 rho delta V plus rho G delta H. Substituting in, we can now say this is our 1.5 times 10 to the 5. Substitute in for rho. Here's our speeds. And then we can add on our rho, G, and H difference. One's at 0, one's at 10, so 10 meters. to get 2.6 times 10 to the 5 pascals. So definitely look at how this equation is employed. This is usually how it's used in terms of a delta V, a change in velocity, and delta H, a change in height. There are many applications of Bernoulli's equation, and they really do describe fluid flow and what happens as fluids move from one place to another. Things like the Venturi meter, curveballs being thrown, or aeroplane wings and how they actually behave and create lift are, between Venturi and Bernoulli, really characterized by these equations. And here we have an actual teardrop-shaped wing as on an aircraft, and as you can see, the air fluid flowing over this wing is creating lift and creating a force F upwards, which would make essentially an aircraft fly. If we're fully characterizing fluids, and this is not a complete course on fluid dynamics, we've got a lot to discuss in this class. So I just want to mention some of these points. This will probably not be on an exam in terms of actually characterizing viscosity, but I do want to mention what it is. Viscosity within a fluid is friction between the different layers of that fluid. In these cases, a pressure drop is needed to force water through pipes, and when the fluids are rubbing against one another, it creates this viscous force which retards the motion of the fluid through the pipes. This is found by a force, which is eta, which is essentially a coefficient of viscosity, an area, the speed or velocity of your fluid to the diameter of the pipe. At a high enough V over D value, turbulence will set in and disrupt the flow of the fluid as it runs through the pipes and end up with a force which holds back your fluid. That's what we refer to as viscosity. And this is really the measure of why oil tends to be thicker than, say, water. It's a measure of its viscous properties. Like I said, we're not really going to look at this in terms of a calculation, but we're going to look at this more from the terms of what it is and knowing its definition. Now, where we've discussed such things as Bernoulli's equation and how that relates, say, to flight, when fluid elements move along smooth paths, then friction is essentially referred to as viscosity in the case of laminar flow. Laminar flow here is essentially dealing with the flow of fluids around smooth objects. We did just briefly mention turbulence. People who fly probably experience turbulence. Turbulence in an aircraft is usually caused by hot air rising, cold air descending, and disrupting the air currents, causing a rougher journey as you fly through different densities of air, and the aircraft has different levels of buoyancy through the atmosphere. If we're looking at turbulence, essentially you can see it here, all of this all these vortices set up, all the flow being disrupted, and this not being a nice, smooth, straight line flow. This is, as it says here, fluid elements moving along irregular paths rather than in nice, straight, linear fashion. So at very high velocity gradients, say when we have a restricted pipe and we're looking at the velocity of a fluid moving very, very quickly, in cases like that, we can see our turbulence increase. So when we're looking at ideal fluids, which all of ours will be, laminar flow, as I said, over smooth objects and things like that, will be a case where you have no turbulence. Non-viscous fluids have no friction between the fluid layers, and if you assume your fluid is incompressible, it means its density is the same everywhere. All of the fluids that we're going to look at will abide by these terms, so we're not going to be too complicated in our mathematics. A couple of final points. If we are moving fluids or moving some form of fluid from one place to another. Molecules in that fluid often move from regions of high concentration down a gradient to low concentration. This is actually obeys Fick's law, and this actually relates to a lot of biological processes or chemical processes. And a diffusion rate through, say, a membrane or something like that is usually characterized as mass per unit time, which is going to be some diffusion coefficient times an area, and then is a differential of the coefficients here over some length. We are not going to employ this in physics terms, but it does relate to fluid flow. And finally, if you are dealing with biological processes, osmosis is another way of moving fluids from one place to another. And this is the movement of, say, water through a boundary while denying passage to other molecules. These tend to be more of a biological application, which we will not get into. What I do want you to make sure you know is what is the definitions of things like turbulence, laminar flow, and why do we assume that our fluids are incompressible.